A first synthesis. Our video on prospectively efficient prices terminated with what we hope might be accepted as a plausible price calculation based on variables that are expected to vary with time. No proofs were offered as to whether these continuously varying prices would in fact guide a generic input-output structure into the unique, equal final, and optimal state implicit with its boundary conditions of production and utility trade-offs. This video makes our case that the SF-econ price calculation will quickly advance a chaotic economic state into close approximations of Pareto optimality, and these calculations will thereafter proceed, for so long as boundary conditions remain constant, to advance the economic state toward ever more refined expressions of the perfect optimum. Model Zero's fundamental operation can be envisioned in terms of one limb of one production function. As shown here, the limb for a good J's input to a sector I's production function will bring one factor input rate, E sub ij, together with its corresponding output rate, Y sub I. The production function's slope at this point, J's marginal product with respect to I, is, by definition, equal to a ratio of J's marginal value P sub ij to I's price pi. Here we see J's marginal product, P sub ij, equated to its derivation in the efficient prices video, which is to say beta sub I over the quantity U sub ij plus E sub ij. Recall also that the prices video had all of J's marginal values among the sectors I, resolved into J's current price, P sub j. With all current prices known, we can readily introduce I's optimal usage rate of J, Q sub ij, into this illustration. This is because we know that optimality occurs where the slope of the production function's tangent equals a ratio of J's price P sub j to I's price pi. Progress toward optimality can now be envisioned as moving asset employments E sub ij ever closer to Q sub ij on every limb of every production function. Our video on the material circuit required that asset replenishment rates R sub ij be set as close to Q sub ij as current supplies allow. This policy will have asset employments E sub ij driven ever closer to Q sub ij over time. Returning to our earlier example, we see that E sub ij is less than Q sub ij, and the value of J to I, P sub ij, is therefore necessarily greater than J's current price, P sub j. As E sub ij is driven toward Q sub ij, J's marginal value to I will decrease, while J's price, being dependent on J's marginal value to the economy as a whole, remains much more consistent. Note that these operations are innately conservative and goal-seeking. Their potential is based on the difference between E and Q, which the model is always operating to decrease. Note also that the ultimate goal of these operations is not revealed until the optimal stasis arrives, should that ever actually happen. The dynamics operating on Model Zero's production functions can also be portrayed entirely in terms of the relation between a good J's price P sub j and the marginal values that J has among the sectors I. Our video on price has these relations expressed in ratios of the sector I's beta parameter to the quantity U sub ij plus E sub ij. J's price was portrayed as the slope of a ray embodying the central tendency among these data. Model Zero's progress toward optimality can now be portrayed in terms of the points expressing J's marginal values, P sub ij, moving ever closer to the central trend line, even while the trend line's slope is being adjusted, owing to the repositioning of the points representing marginal values. If it can now be agreed that Model Zero's price calculations must always tend to unify prices and marginal values, we can move on to question whether or not these calculations will efficiently conduct the economic state to optimality. So far as we know, this question cannot be answered in the abstract mode characteristic of much economic discourse. All we know how to do is build objective emulations that give tangible expression to our suppositions about economic causality. One of our simplest emulators operates on an isolated input-output array, representing the interactions among just 3 sectors, 2 industries, and 1 household. In the most obvious experiment to be performed on such a system, an initial equilibrium is disturbed when Sector 2 is suddenly made a more efficient user of all its inputs. One of the time series generated by this emulation brings together all the indicia of value associated with Sector 2. Here we see the marginal value of good 2 to the household sector traced in yellow, its marginal value to Sector 1 in blue, its marginal cost of production in green, and its transactions price, P sub j, in red. By our estimation, these series indicate a business cycle of approximately 5 years. Our readings on the empirics of business cycles suggest that the minimum recorded cycles are just less than 6 years. If these estimates are acceptable, then it would seem that the simulation is at least as efficient as the economy ever gets. And SF-Econ offers dozens of emulators against which to test our thesis that Model Zero computes efficient prices, irrespective of the degree to which equilibrium might be in evidence. Our final synthesis of Model Zero will complete the signal path developed in our video on the material circuit. At this point, we know that a material circuit is completed when output rates Y operate to replace assets being used up in production, that is, the employment rates E sub ij. Asset replenishment rates R sub ij control this process through optimal distributions of the goods J among the sectors I. Development of the material circuit ended with the optimal rates Q sub ij still to be specified. That specification began with the determination of prices P sub j. As laid out in our video on that subject, parameters beta were derived from the model economy's current state, epsilon E, and its boundary conditions, ZU. And then there ensued a process involving values of marginal product and leading to commodity prices P sub j. With prices determined, parameters zeta can be computed, as per our video on the polynomial factoring problem. That video detailed the calculations through which zeta combines with the boundary conditions, ZU, to determine the optimal rates Q sub ij for a sector I to use good J. With Q sub ij known, actual replenishment rates R sub ij can be set with reference to available supply, as determined by current market levels M sub j, and output rates Y sub j. Operation of the model is then shown to eventuate in cell-for-cell equality among the matrices Q sub ij, R sub ij, and E sub ij, just as market variables M sub j become null. Animation of this signal path can be envisioned by a simplified reconstruction. First, we portray the model's current state, epsilon E, interacting with its parameters ZU to determine prices P. This operation is referenced by the symbol beta, developed in the video on prices. We then portray the parameters ZU interacting with prices P to determine the system's optimal state variables Q. This operation is referenced by the symbol zeta, developed in the video on polynomial factoring. Though the model operates to resolve Q with E, we cannot make a direct substitution of Q with E, 1, because this would create a circular reference, and 2, current prices are not necessarily optimal at this or any arbitrary point in time. So our closure of Q with E must be dynamic, as indicated by the integral symbol, which is intended to reference the videos explicating the financial and material circuits. The integration advances the system state variables E through one differential element of time. This new state can then figuratively replace the prior state in our calculation and become the basis for advancing the system state yet again. Once these operations are programmed, they can be allowed to proceed indefinitely to create the impression of time's passage.